Okay, so welcome to the Arc Science seminar, and today's speaker is Samrith from IIIT Delhi, and he's going to talk about set partitions, Tableau, and subspace profiles and regulars with semisimple matrices. Samrith.
Okay, thanks, Amri. Uh, thank. So today's talk is going to be an enumerative combinatorics talk. So, well, the title is more or less self-explanatory, but I'll go into it a little bit in detail, especially the last part. Okay, so let's begin with set partitions. So let P denote the set of positive integers and S be some subset of P. So partition of S is simply a decomposition of S into subsets A1 up to AN that are pairwise disjoint and non-empty. So the shape of a set partition is simply the list of cardinalities of its blocks sorted in weakly decreasing order. And it will, so for instance, if A is the set partition whose blocks are 1, 2, 3, 6, 7, and 4, 5, then it has shape 3, 2, 2. So this set partition is written in standard notation, which means that the entries in each block are increasing and the blocks are sorted in increasing order of their smallest element. So it will be convenient to denote a set partition of this kind by an array of numbers. So the rows correspond to the entries of the blocks. And I guess it's kind of clear. And this array comes from the standard notation. So the first column is always going to be an increasing sequence. Okay, so let pi-s denote all set partitions of S and set partitions of a given shape lambda that will be denoted by pi-s lambda. So a tableau is simply a finite array Tij of positive integers. So we think of it as taking the Young diagram of the partition lambda and filling the cells with positive integers. So here is an example. So that's a tableau of shape 432. And the support of T will simply be the positive integers that occur in T. So we'll say that a tableau is multilinear if each positive integer occurs at most once in T. That is, entries are not allowed to be repeated.
Sorry, what's P? This math.
So P is the set of positive integers.
Okay. Okay, thanks.
Yeah. Okay, so P is, so the it's multilinear if each entry appears at most once, and the rows and the columns of T are increasing. Okay, the rows are increasing from left to right, and the columns are increasing from top to the bottom. But please feel free to interrupt me at any time if there are any questions.
Okay, I will. So, sorry, so there is something called standard. Okay, I'm not obviously an expert, but there's something called standard Tableau, right? And that involves.
Right. So it's standard if your entries are precisely the positive integers from 1 to n. All included.
Here you can jump across and so on. Yeah, there's no need.
Yeah, so here there may be some, the entries need not form a contiguous subset of the positive integers.
Or an initial subset either. Yeah, right.
Yeah, or even an initial subset. Yeah.
And also what is, I mean, any sort of, maybe you'll explain it to us later what the multilinear stands for. Like
okay, so this multilinear is kind of like, well, each appears at most once. So it's like those multilinear functions where you have a sum of products, right, and powers can't exceed 1. So entries can't be repeated more than once here.
That's when you do, for example, when you convert it to a weight, you get a square free monomial. Right?
That's right. That's right.
Thanks.
All right. So tab S will be the set of multilinear tableau with the support S, and tab S lambda will denote those multilinear tableau with the given support and shape lambda. All right. So it turns out that there is a nice way in which one can associate a tableau to a set partition. So let's start with our running example, the set partition shown here. And let's sort each of the columns.
Sorry, in your previous thing, lambda is a partition, right?
That's right. Lambda is an integer partition.
Okay, okay, thanks. Is the usual definition of Tableau.
Exactly. Yeah.
Okay.
The usual. Yeah. Okay. So here is a set partition, and the diagram of the set partition is here. So what we want to do is sort the columns individually. So for instance, 1, 3, 5, 2, 6, 8, and 9, but also top justify the cells after they are sorted. So starting with this array corresponding to the set partition, one obtains a tableau. It's actually not difficult to see that this is a multilinear tableau. So by construction, the columns are going to be increasing, but it can also be seen, for instance, by an inductive argument that the rows are increasing as well. So this operation will give a tableau, associates a tableau to each set partition. So we'll denote that by TA. TA is the tableau corresponding to the set partition A. So A going to TA, well, if the set partition has shape lambda, then the shape is preserved. So if you start with the set partition in pi s lambda, then you obtain a tableau in tab s lambda. And moreover, this map is surjective because given any tableau of shape lambda, you could simply look at the set partition whose blocks are the rows of that tableau. So that is clearly a surjective function.
I have a question. Is it known what the cardinality of the inverse image of each tableau is under this map?
Okay, that's a nice question. I am in fact coming to that in a little bit.
Okay.
I'll explain that. Yeah. All right. So let pi t denote the fibers of this map. That is, given any tableau, look at all those set partitions in pi s lambda that map to this given tableau. So for instance, let's look at an example. For instance, so of course, multiple set partitions could map to the same tableau. For instance, if you have this tableau, then this is an exhaustive list of the pi t is given by all of these set partitions written in standard notation. In this case, there are 6 set partitions mapping to this tableau.
Sorry, could you work? So I don't. The very first one on your list, I don't quite get it. So how does that lead to this? I didn't quite understand the previous. So 1, 2, 9, 3, 3, 8, 5, 6. If I write, so what do you mean by that? Could you just work it out, please?
Sure. Sure. So here is the idea. So if we were to write that down, so we begin with the array as we did here. Okay. So the first step. So you write down the blocks of the set partition as the rows in an array. And then you need to sort the columns individually. The first column is already sorted, but the second column when sorted will give me 2, 6, 8.
I see. Okay. Sort the column means that. Sort the column means that. Okay.
Exactly. So sort the column such that it's increasing from top to bottom.
Okay, fine. Yeah.
So for instance, here the entries in the second column would be 2, 8, and 6, but that would sort to 2, 6, 8.
Okay, got it.
All right. So these are all the set partitions that under sorting columns and top justifying the cells will give you this tableau. So one can ask, what is the cardinality? Like how many set partitions, as Sridhar asked, how many set partitions map to a given tableau? Well, so that's not difficult to compute. So for each cell in the Tableau, excluding the cells in the first column, so let's defineCijt. So that's simply the number of cells in the previous row. So Tij, soCijt is associated to this entry Tij. Look at the entries in the previous column that are in a row I or greater, which are less than the entry Tij. That is Cijt. So I'll come to an example shortly. And Ct is simply the product of all theseCijs, as I and j vary over all the cells except the cells in the first column. So for instance, for the example above, so let's so the first column there are noCijs defined, but the very first entry in the second column, which is 2. So the entries in the previous column that are less than 2 is simply 1. So that C1, 2 is simply 1. Okay, similarly for the element 6, all 3 are less, but in rows higher than 6, only 3 and 5. Okay, so in the previous column, 3 and 5 are less than 6. That gives us a 2 corresponding to the entry 6. I hope that this is clear. Okay, similarly, the rest of the entries are filled.
Why is it 1 for 8?
Well, so 5 is the only one less than 8. So you look at entries in the previous column, but in rows greater than or equal to this row.
Oh, rows greater than or equal to. Oh, I see.
Exactly. So Cij is I prime greater than or equal to I, and Ti prime j minus 1 is less than Ti.
Okay. Yeah, I missed that.
Look at the elements in rows, same row or higher row. And it can be shown that this Ct, which is the product of all of these entries, so is in fact going to give us the cardinality of pi t, which is what the next theorem says. So in this case, Ct is, well, the product of these entries, which is 2 times 3, it's just 6. Okay, so for any Tableau, the cardinality of this pi t is simply given by Ct. So this gives us some interesting corollaries. So if one sums up this Ct over all Tableau of, so these are now standard Tableau. Let's consider standard Tableau whose entries are 1 to n. And if you look at standard Tableau of a given shape, we know that set partitions of a given shape map to Tableau of the same shape. So summing up Ct will count over all Tableau of shape lambda, standard Tableau of shape lambda will give you all set partitions of shape lambda, set partitions of the first n positive integers. And if one further sums the previous quantity pi n, the cardinality of pi n lambda over all partitions which have precisely m paths, then one obtains all set partitions of an n element set into m blocks, the number of partitions, which is simply the Stirling number of the second kind. And if you simply sum over all Tableau, whereas taking all shapes into account, then one gets the total number of set partitions, which is the Bell number, which is the definition of the nth Bell number. So one can ask if there are Q analogs of this. Can one come up with a Q analog for the previous results? So it turns out that if one defines CQT, so we had these integers Cijt coming from the entries, the cells in the Tableau. So suppose one naively replaces each of those integers in the product by the corresponding Q integer. So the Q analog of the integer n is simply the sum 1 plus Q so on up to Q to the n minus 1. So if you define CQT to be the product of these Q integers, then it turns out that, so first of all, it is clear that this CQT has integer coefficients. And well, when we plug in Q equals 1, we simply have the product of theCij's. So that is simply CT. So let's define this B lambda Q by summing CQT over all standard Tableau of shape lambda. Then, well, so the evaluations of B lambda at 0 and 1 are easy to compute. Well, if we put Q equals 0, then so the CQT simply reduces to a product of ones. So it's simply 1. So B lambda at 1 is, B lambda at 0 is simply the summation of 1 over all standard Tableau, which gives the total number of standard Tableau of a given shape. While if we throw in Q equals 1, CQT reduces to CT, and by the previous corollary, summing CT over all Tableau of shape lambda simply gives you all set partitions of shape lambda. So these are two specializations of these polynomials.
So if the shape of lambda is 1, 1, 1, 1, mean it's just a column, then it's CT 0.
Its CT will be 1. So the empty product, we take it to be 1.
Okay.
All right, it's going to be the empty product because there are no cells in columns higher than 1. We take CT to be 1.
Oh.
All right, so the interesting question one can ask here is that since this B lambda at 1, it reduces to the total number of set partitions of shape lambda, then can I give some statistic on set partitions, which if I sum will give me these polynomials B lambda Q? That seems like a natural question. So it turns out that that is indeed the case. To explain what the statistic is, so let P star denote positive integers with one symbol infinity adjoint, where we will deem infinity to be greater than all other elements of P. So given any 4 distinct elements in P star, we'll say that the arcs AB and CD are crossing if well, A is less than C is less than B is less than D, or C is less than A is less than D is less than B. So the non-crossing versions are on the left side, and the crossing versions are depicted on the right side here. All right, so one can define an interlacing. So given any set partition, so our running example as before, we'll say that there is an interlacing if the jth arcs cross for some j. So let me define what these jth arcs are. So the first arcs correspond to the first 2 elements in each of the blocks, and they're all drawn in the same color here. So first plot all these entries 1, 2, 9, 3, 8, 5, 6 on the number line, and add the point infinity. So the first arcs correspond to the 2 smallest elements in each of the blocks. So 1, 2, 3, 8, and 5, 6. So the second arcs are indicated in orange here. So that will correspond to 2, 9. So for each of the other blocks, since there are only 2 elements, after 8, you add the point infinity, and that gives you the second arc. Similarly, 5, 6, infinity. So the second arcs are 2, 9, 8, infinity, and 6, infinity. So those are all indicated in orange. And the first block has a third arc coming from 9, infinity. So the first arcs are all in the same color. The second arcs are all orange, and so on. So usually crossing corresponds, so an interlacing is a crossing of jth arcs. So for instance, here, there are two crossings of orange arcs, but there are no crossings of green arcs. So if VA is the number of interlacings of this set partition, then VA is simply equal to 2, coming from the crossings of the orange arcs. The crossing between the green and orange arc is not counted here. Okay, so this is a variant of the some kind of variation on the crossing number, where you look at all possible crossings irrespective of the position of the arc. So this VA
Sorry,
is,
I just have one question. In the previous diagram, if there were a crossing of green and green, that would also count?
exactly. So any crossings of greens or any crossings of oranges or any crossings of blue, all of
And
those.
what is the edge from 9 to infinity? What does that mean?
Then the edge from 9 to infinity is indicated there. So that is the third arc in the first block. So to all of the blocks, you adjoin the point infinity at the end and you draw an extra arc starting from the largest element of that block.
Okay, thanks.
All right, so it can be shown that this CQT, you can in fact obtain this CQT by summing over all set partitions which correspond to this tableau, this interlacing number Q to the VA. So VA is the interlacing number that was just defined.
No. What? So if you have crossings between green and crossings between, you just sum the crossings. If there were crossings.
That's right. The total number of crossings is what you sum to get VA.
Okay.
Okay, so the interlacings of the total number of interlacings of the first arcs plus the total number of interlacings of the second arcs and so on. So you need to sum over.
Yeah. Okay, got it. Thanks.
Sum over G. Yeah.
Sorry, is it possible to have crossings between arcs of the color blue?
Arcs of the color?
Blue, like 9 to infinity.
Well, in this particular case, there is no crossing, but in general, arcs going to infinity can cross.
Okay.
Arcs going to infinity can cross. That's true. It won't happen when the blocks are of the same size, but if the blocks are of different size, then the arcs can cross.
Like, I think 2, 9 crosses 8 infinity here and 6 infinity. So.
Okay. So I guess I meant to say by cross, I meant interlacing. Okay. So interlacing versus crossing. I should probably make that.
No, it's fine. Exactly right. I mean, the arc with an infinity interlaces an arc of some other block. Not.
So do arcs to infinity will cross ever?
You can see them crossing here, right? The arc from 2 to 9 is crossing.
So 2 to 9 and 8 to infinity are interlacing.
No. I guess what they mean is if infinity is the ending point of two arcs, they will not cross.
Well, they
do. Exactly.
So that has actually happening here.
Where?
Okay, so in this particular example, it doesn't happen.
No, it doesn't seem to happen in general either.
What he's saying is if both arcs are to infinity, then they are not crossing. It won't match the definition of crossing.
That's right. If both arcs end at infinity, then they cannot. That's right.
That's what they were trying to say.
Okay, sure. Agreed. That's indeed true. All right. So this CQT, it can be shown that you can obtain this CQT by summing this interlacing statistic over all set partitions which correspond to this tableau T. So one can ask, what are the non-interlacing partitions? So non-interlacing would correspond to this VA being 0. So if one looks at the theorem here on the left-hand side, we know, well, on the right-hand side, Q to the VA would be 0, would give you the constant terms in the polynomial on the right-hand side. But we already know what the constant term in CQT is. CQT being a product of q integers, its constant term is simply equal to 1, which means that for each tableau, there is precisely one set partition that is non-interlacing and corresponds to that tableau. In other words, non-interlacing partitions of shape lambda are in bijection with standard tableau of shape lambda. So one can take this one step further. So if we sum over all possible partitions, so the if one uses the Robinson-Schoenstatt correspondence, then non-interlacing partitions overall are in bijection with involutions in the symmetric group, Sn, which is simply the total number of tableaux. All right, and now if we sum the CQT over all tableau of shape, well, over all set partitions, if we sum Q to the VA, then we obtain this B lambda. Simply because
when you say are in, okay, 1 second. Yeah, when you say are in bijection, just mean that the numbers are the same? Or?
Yeah, exactly. The numbers are exactly the same.
Okay. No, not that there is a natural bijection between them. You're not suggesting that.
Okay, so there is also a natural bijection which one can give. So one can, so one simply needs to say what is the arrangement for a given tableau, right? So if one goes back here, right? So there is a unique way in which one, so if one wants all these, so what am I trying to say? Just a second. Sorry. So yeah, so these q integers all have constant term 1, and picking the terms 1 sort of will give you, so for this tableau, if we want the corresponding partition that is non-crossing, then I guess one needs to look at the set partition that you'll obtain simply by sorting the columns in decreasing order, but also making sure that the rows are increasing. So it turns out that there is a unique way to do that. So one can actually explicitly say what the bijection is, but maybe I'll not go into that right now. Maybe at the end of the talk, we could discuss that.
Yeah, sure.
One could, in fact, give say what the bijection is in this case. All right. So, okay. So it turns out that these polynomials B lambda, when evaluated at -1, those are always positive. So one can ask if there is a combinatorial interpretation of that fact. And it turns out that the value at -1 simply counts the number of so-called standard shifted tableau. So maybe this is best explained with an example. So if lambda is the partition 3, 3, 1, then a shifted tableau is simply, so take the Young diagram, but except that the rows will all have the same length, except that now we indent each row one step to the right, one cell to the right with respect to the previous row. So for instance, the 4 tableaux shown here, these are all shifted standard tableau of shape 3, 3, 1. So for instance, in this case, we have B lambda given by this expression, and B lambda -1 turns out to be 4. And in fact, there are precisely 4 standard shifted tableaux of that shape. And those are all shown here. Okay, so basically, we still want that the rows and the columns are increasing, and the diagonals are increasing as well. So the diagonals in this case being 1, 4, 7, 2, 5, and so on. So the specialization at -1 counts standard shifted Tableau. So here is just a list for the partitions of 6 of these polynomials b lambda q. The constant terms are given by the dimension of the partition. The sum of the coefficients should give us the total number of set partitions of that shape. And the alternating sum of the coefficients should give the number of shifted Tableau. So we have 3 specializations for these polynomials. To give another, one can give some more applications of these b lambdas, but I'll come to that in a little while. Oh, this is just a value for a particularly large partition. Okay, this is
maybe this is a stupid question. Seemed like quite -2 also the list seemed positive.
At -2 as well, is it?
It seemed like that to me. I don't know if.
I see.
I guess that's not clear. I mean, it's clear that at -1 it will be positive because the q integer is either 0 or 1 at -1.
Right.
But at -2, q integers can be negative. In fact, I suppose odd q integers.
Oh, I see. So that itself. I see.
So if it is positive, it would be surprising.
Okay.
In fact, I think at 2, 2, 1, 1, that is probably negative. I'll have to check that, but I think that may be one partition where it's negative. I'll have to check anyway. Anyway, in general, it's not immediately clear why it should be. Yeah. My guess is that it probably isn't. Yeah.
Okay.
So Raghunath, 2 to 2 is negative, right?
Sorry?
2 to 2 seems to be negative.
2 to 2 seems to be negative. I see. Okay, thanks. Sorry for that stupid question.
Yeah. All right. So, okay. So one can relate these b lambdas to these q Stirling numbers of the second kind. So let me quickly explain what those are. So recall that SNM is the number of set partitions of n into m blocks, of an n element set into m blocks. But these can also be interpreted in the context of rook theory as the number of ways to place n minus m non-attacking rooks on a staircase board of size n. So a staircase board of size n is simply the Young diagram of the partition n minus 1, n minus 2, so on, all the way up to 1. So in this case, we have the Young diagrams of the partition 3 to 1. And rooks, well, rooks are attacking, 2 rooks attack if they are well in the same row or in the same column. So number of ways to place 2 rooks in this case on the staircase board. The Stirling number, this is one interpretation of the Stirling number. So a Q analog of these Stirling numbers can be defined. So the Stirling numbers satisfy a recurrence, and which is simply that SNM is Sn minus 1 m minus 1 plus m times Sn minus 1 m. If one simply replaces the m by the Q analog, then one obtains these so-called Q Stirling numbers. So they are defined by this recurrence and with some initial values given by the canonical value. All right, so in analogy with these rook placements, so Garcia and Remel showed that these Stirling numbers of these Q analogs of the Stirling numbers of the second kind can also be computed from rook placements. So let's take the same example as before. But now what we do is that we mark with a dot all those cells that are below or to the left of some x. So for instance, in the first figure, that gives us 2 dots. So for each of these diagrams, we do that. And the blank cells that are left over gives us the power of q. In the first diagram, there are 2 blank cells. that is cells that are not marked with an X or a dot. And those correspond to the powers of Q here. So summing up these powers of Q over all these rook placements on the staircase board, n-1, n-m rooks on the staircase board, gives us the Q analog of the Stirling number. Well, I should mention here that one should suitably normalize it. Should normalize it such that the constant term comes out to be 1. Sorry, such that there is no power of Q. Pull out all possible powers of Q, and in the end, you get what you get is the Q Stirling number, SQNM. So set partition statistics that generate these numbers have been known for a while. Notably, they appear in the work of Garcia and Remmel, Wax and White, and also Kai and Reedy in a more recent paper. So in this spirit, we also produced some statistics which allow us to generate the Q Stirling numbers of the second kind. So here are some ways to express this SQNM as sums over. So it turns out the first equation gives a way to write these SQNMs in terms of the polynomials B lambda by summing over all partitions with length m. And since B lambda can be written as a sum over the CQs, that gives us the Stirling numbers as sums over Tableau, which is the second equation here. And if one goes, uses the connection between Tableau and set partitions, then one can obtain these Stirling numbers by summing a statistic over set partitions. So here pi nm is all partitions having m blocks of the first n positive integers, whereas these lambda I superscript a, the sequence simply denotes the shape of A. All right, so how much time do I have left?
You have 22 minutes.
22, okay. All right. So, all right, so here is an interpretation where a combinatorial interpretation of the Stirling number of the second kind in a finite field setting. So suppose we
sorry, could you go back to the previous slide? If I'm not interfering into your time. So what is this lambda I to the power A? I'm lost. I mean, A is a set partition, right?
That's right. So lambda I superscript A, that's simply a superscript. It simply indicates.
Oh, it's just the, okay. It's just the partition.
Yeah.
Okay. Thanks. Yeah.
Just a way of writing it. Yeah. All right. So let V be some vector space over FQ. And suppose we have a sequence of lines in V. So L1 to Ln, which simply one-dimensional vector spaces of V. So given such a sequence, one can obtain a complete flag of dimension k. Simply look at the subspaces spanned by say L1, L1 and L2 and so on, and delete the repeated subspaces in that increasing list of subspaces. That will give a strict containment of, and that is simply a flag of dimension k for some k. So if you have a flag of dimension k and you fix an ordered basis, and the group of unitriangular matrices acts on this.
I mean, I'm lost. I mean, L3 could be contained in the span of L1 and L2, right? I mean,
that is true. That's possible.
So what do you mean by complete?
So L3
complete flag of dimension k could be
so the dimension, this k need not be equal to n.
Okay, so you collapse. Okay, fine.
So whatever subspaces are repeated, you just simply throw them out so that you get a strict containment.
Okay.
So if you have a complete flag and you pick a basis, then the group of unitriangular matrices over that basis will act on these sequences of lines which generate the flag. And the number of orbits under that action is simply these Stirling numbers of the second kind. These were studied by Milne in a sequence of papers. In fact, these Q Stirling numbers go back much earlier. I think they were initially introduced by Karlitz in a very early paper, I think 20s or 30s. But I think this combinatorial interpretation, the first combinatorial interpretation in a finite field setting, is probably due to Milne. For yet another interpretation, there is this recent paper of Kai and Reedy that I alluded to earlier. They show that this is simply the rank generating function in a poset that you can define on restricted growth words. So these restricted growth words will correspond to the set partitions of n into m blocks. All right, so let me define subspace profiles. So to look at another interpretation of these B lambda Qs over finite fields, and to also give another interpretation for these Q Stirling numbers over finite fields, we define the subspace profile. So FQ is as usual the finite field with Q elements, and delta is some linear operator on FQn. So let's say that a subspace W has partial delta profile mu1 up to mu k. If the dimension of W plus delta W all the way up to delta to the j minus 1 W is given by the sum of the mu i's 1 through j, for each j going from 1 to k. In addition, we will say that that's a complete profile, or simply delta profile mu, if those dimensions stabilize at the kth step. In other words, it stabilizes at this stage. So the dimensions are the same. Okay, for instance, if you take an invariant subspace, then its delta profile, its profile is simply the partition with a single part equal to m. Whereas if you have a subspace that is spanned by a delta cyclic vector, that has a profile 1 to the n. Okay, so basically, probably, so delta cyclic vector would span the whole space. So that corresponds to the partition of all ones. One can also show that these mu j's are weakly decreasing, and therefore this mu is a partition of some integer that is less than or equal to, which is the dimension of the vector space. So if so, let sigma and mu denote the number of subspaces with a given delta profile mu. Then it can be shown that this sigma and mu is a polynomial in Q that depends only on the similarity class type of delta. So recall that to say what the similarity class type is, simply recall that delta acting on column vectors in FQN simply gives us a module structure, which is defined by some irreducible polynomials and the corresponding partitions. So the type is simply the similarity class is given by these irreducible polynomials and the partitions. The type is simply where you're not interested in the polynomials, the irreducible polynomials, but simply their degrees. So the type is the conjugacy class data consisting of the degrees of the irreducible polynomials and the corresponding partitions. So this notion goes back to the work of Green on the characters of the irreducible characters of the finite general linear groups. Well, the point is that the number of subspaces with a given profile only depends on the type of the operator. So that's what the theorem says. And in particular, when this operator is regular split semisimple, then one can give an explicit formula for the number of subspaces with any given profile mu. And it's given by a product of powers of up to factors of q and q minus 1. It's simply given by these polynomials, b lambdas. Okay, here mu prime is simply the conjugate of the partition mu. So one can also use this to give a combinatorial interpretation of these Stirling numbers. So if you are given a subspace, any subspace W, so let RW denote the dimension of the smallest delta invariant subspace which contains W. Therefore, it's simply the dimension of the sum delta to the JW as J varies. And it can be shown that when delta is regular split semisimple, the number of subspaces of dimension M such that R of W is any given R is in fact given by n choose R times Q minus 1 to the R minus M times SQRM. And this interpretation allows us to give a bijective proof of an identity of Carlet's that goes back to his, this is his original paper where he introduces the Q Stirling numbers. So, well, probably this is not the original paper. Maybe this is the second paper where he talks about them. So he has this identity that expresses the Gaussian binomial coefficients as sums over Stirling numbers. So this can simply be done by counting all n-dimensional subspaces of the n-dimensional vector space by summing over these possible values of Rw. And for a given R, we know that there are precisely the number of such subspaces is simply the summand inside this summation. So that gives a bijective interpretation of this identity. All right, so closely related to this idea of profiles is what is called splitting subspaces. So a splitting subspace is of FQN is a subspace W of dimension M such that the direct sum W delta W up to delta to the D minus 1 W is the whole vector space, where of course we take D is n by n. Of course, here we need the dimension M to be a divisor of the dimension of the ambient vector space. So this corresponds to the subspace W having profile simply M to the D. That is a partition with D parts all equal to M. So splitting subspaces were introduced by Niederreiter in the context of pseudo-random number generation. So they are also relevant in the theory of Krylov subspaces. And those seem to have applications in several areas. For instance, I think the algorithm to compute the minimal polynomial of a matrix would use Krylov subspace methods. And I believe that they are also used in the general number field set for factoring numbers. All right, so if you are given an arbitrary operator, then one can ask, what is the number of splitting subspaces of a given dimension? So this problem is open, and it's still open. But there are a few operators for which this precise answer is no. All right, so let's denote by sigma m d delta. So let's assume that the dimension of the vector space is m times d, and let sigma m delta denote the number of m-dimensional delta splitting subspaces. So one can see that this depends only on the similarity class of delta. In fact, this is somewhat redundant here because we already know that the number of subspaces with a given profile is, well, it only depends on the similarity class type. But nevertheless, there is an explicit bijection here between the delta splitting subspaces and S delta S inverse. So if two operators are similar, one can in fact provide an explicit bijection between the splitting subspaces, m-dimensional splitting subspaces for both operators. All right, so maybe there's some stuff here that I'll quickly skip over in the interest of time. So let me state this problem on Krylov subspaces. So suppose one is given m vectors in FQN. So the Krylov subspace generated by S is simply the submodule spanned by those vectors, where you view FQ to the n as an FQX submodule, as an FQX module, sorry, under the action of delta. So let kappa m delta denote the probability that the Krylov subspace spanned by these m vectors is the whole vector space. Okay, so there are m tuples. To each vi, there are q to the n possibilities. So the denominator q to the nm is simply the total number of such tuples. But we want to see what proportion of these tuples actually generate the whole space under the action of this operator delta. So this km delta is the probability that if you choose m vectors at random, that they will generate the whole space. And this probability can be given, can be precisely estimated in the case where delta. All right, so I should probably say what the Frobenius index of an operator is. So the Frobenius index of any operator delta is simply the number of summands in a cyclic decomposition for delta. Or at the level of conjugacy class data, it's the maximum length of a partition that appears in the conjugacy class data for this delta. So if one is given the minimal polynomial, then one can compute this probability precisely, as Brent, Gao, and Lauder showed.
Is it the number of blocks in the rational canonical form?
Exactly. It's the number of blocks in the rational canonical. Exactly. Okay, so this can be estimated. Now, truncated Krylov subspaces are what are more interesting, apparently, from a practical point of view. So they are defined in the following way. So pick this subset S as before of m vectors. Now the Krylov subspace generated by delta, but truncated to degree d, is basically all sums fi delta on bi, where so earlier fi could be arbitrary polynomials, but now we insist that their degrees are bounded, strictly bounded above by d. And again, one can ask, so what is the probability that if you select m of these vectors, that the detruncated Krylov subspace spanned by these vectors is all of v? And that is an open problem. Okay, it has been stated to be quite a difficult problem, and there are some specific cases where an answer is known, but maybe I'll come to them in a little bit. It is possible, however, to express this probability in terms of the number of splitting subspaces, and this is not difficult to prove. So being able to compute the number of splitting subspaces, the sigma md delta, will give us the exact value for this probability. So here are cases where one actually knows the number of splitting subspaces. So Chen and Seng proved in their paper in finite fields that if this operator has an irreducible characteristic polynomial, then the number of splitting m-dimensional splitting subspaces is well given by this formula. And in this is another recent theorem. This is joint work with my PhD student Divya. So if delta has type, so recall that the type is given by tuples, the degrees of the polynomials and the partitions. So this is the case where the partitions are all rectangular. So m parts all equal. So if we set D to be the sigma di ei, which would simply be the degree of the minimal polynomial corresponding to this type delta, then one can give a precise expression for the number of m-dimensional delta splitting subspaces again. And for yet another case, suppose you have a type where all partitions have at most m parts and which satisfy a certain condition on the mth part, that is di times the mth part of each of these partitions adds up to d minus 1. Then it turns out that one can again compute this the number of splitting subspaces. All right, so these are some known cases. So the case where delta is regular split semi-simple was something that we were able to settle recently with using these polynomials b lambda q. So when delta is regular split semi-simple, the number of splitting subspaces is given by these. Essentially these polynomials b lambdas up to powers of q and q minus 1. These b lambdas are as defined before. An interesting case is when d equals 2, namely you have this set partition where all the blocks, there are m blocks, each of cardinality 2, and that corresponds to chord diagrams on 2m points. And in this case, interlacings correspond precisely to crossings. So this polynomial was actually studied by Tusha, who gave a very nice formula for these polynomials in this particular case. Here, interlacings and crossings coincide. And he was interested in studying the number of chord diagrams with a given number of crossings, which corresponds precisely to this case. Okay, this is pretty much what I had to say for today. Thanks.
Thank you, Samrith. We'll open it up to questions. If you have a question, just please feel free to unmute and ask.
So aside from this profiles, so I'm just trying to understand the main result. So it is split semi-simple. Then for any profile mu, you have the explicit polynomial. Is that right?
That's right. So these b lambdas, which are defined as a statistic over set partitions, also count up to these factors of q and q minus 1, the number of splitting subspaces, or in fact for any profile, as I stated a bit earlier, I guess. Yeah, this is the
okay.
Number of subspaces with a given profile under this operator is counted by these b lambdas. Yeah.
Okay. And so the special case of the rectangular partition becomes the splitting subspace problem.
Exactly. So the splitting subspaces correspond to the rectangular, the profiles being rectangular partition. That's right.
Okay. Thanks.
So I had a question on the evaluation of b lambda at -1. You said it's the number of shifted tableau. So is there an RSK way of seeing that?
Is there an RSK way of seeing that? Is it?
Like an insertion mechanism.
I see. That's an interesting question. I'm not sure there's an RSK way to see that.
The proof you have is not combinatorial.
So the proof is actually combinatorial. So, well, it corresponds. So these B lambdas are defined in terms of these Q integers, right? So the Q integers at -1, they behave very nicely. They're always either 0 or 1. So it boils down to summing, rather than summing over all Tableau, it corresponds to summing over certain Tableau, a subset of Tableau of a given shape. And then it turns out that those Tableau are precisely these standard shifted Tableau. This is actually not difficult to prove once one has the interpretation of B lambda as the sum of the CQT over Tableau.
Okay.
I think this problem of counting standard shifted Tableau goes back to Schur and Thrall. Thrall was also interested in enumerating.
So at Q equals 0, right? You get standard Tableau.
That's
And,
right.
Given a standard Tableau, there's a way to construct a non-interlacing, a unique non-interlacing set partition.
Right.
I'm not sure what Sridhar meant by his question, but I'm wondering now if there's any connection with this. So one way to construct the set partition is to construct it step by step. At each step, making sure that you don't allow any interlacing.
Right.
No, I just asked because there's a insertion mechanism by Sagan on shifted set partitions.
This is also for already for Tableau, right? I mean, they correspond to involution.
Right.
So we could already ask that question even for Tableau. Is there some way to relate these non-interlacing set partitions? But for Q equals -1, I don't know which Tableau. So there's a bunch of Tableau with with a bunch of set partitions with statistic which becomes +1 and with statistic that becomes -1, and they cancel out, leaving only this one. So is there some specific set partition that we can point to and say this is the one that corresponds to this shifted Tableau? Is sort of a variant of Raghavan's question. Is there a bijection between a certain class of?
Yeah, I think one can get that bijection simply by, so you take this shifted Tableau and you unindent. So they're all indented, right? If you unindent, you still get a Tableau.
Yeah.
And the set partition corresponding to the unique non-interlacing set partition corresponding to that Tableau is probably what corresponds to this shifted Tableau.
Okay. So they correspond to Tableau, which upon indenting the line, all remain give shifted Tableau. That's basically what.
Right. Exactly. Yeah.
Sorry, another random question. So this partitions, are they, I mean, is there a representation theoretic interpretation or way of seeing them? I mean, just like standard Tableau would be, let's say, the irreducible.
Right. So you are saying, do you mean just non-interlacing partitions or generally all set partitions?
No, I guess I was wondering about the map which associated to each set partition corresponding standard Tableau, right? The one whose fibers you are looking at.
Right.
So I'm wondering whether, I mean, right-hand side is sort of a representation theoretic object. It's a combinatorial.
Right.
So is there something on the left-hand side as well? The set partitions themselves? Is there some way of thinking of that as?
Yeah, that's an interesting question. Again, yeah, I'm not sure. Yeah, I don't know. Set, so some representation theoretic interpretation of set partitions.
Yeah, I mean, is it some basis? So I don't know. Sridhar probably had something with Big Joy, and is that related to set partitions? Anomaly or Sridhar?
They are actually, the entries are itself set partitions or multi-set partitions.
Oh,
in a normal Tableau where you put as an entry the integers, now you replace the integers by some set partitions or multi-set partitions, and that makes set partition Tableau and multi-set partition Tableau. So the convention are different.
Okay.
Okay, I see.
Okay, thanks.
I just had a minor question. What is the bijection between non-attacking rook placements and set partitions?
Here is it non-attacking. Okay, so this one, right?
Yeah.
So this is non-attacking rooks. Yeah. So what you can do is number these columns. Okay. So you throw in the numbers from 1 to 4. So 1 at the bottom of the first column, 2 at the bottom of the second, 3 at the bottom of the third, and 4 to the right of the first row. And then a cross in any position indicates that those correspond. So any cross corresponds to two numbers. Those two numbers should be consecutive elements in the same block. I think that is the bijection with set partitions.
So the first diagram will be 1, 4, and 2, 3.
Exactly. So the first diagram will correspond to 1, 4, and 2, 3. That's right. Whereas the second one would correspond to, well, 1, 3, and 2, 4.
So staircase of size n means it has n minus 1 rows.
Right, n minus 1 rows. So the, yeah.
But it has. Okay, so are there any more questions? Well, if there are no more questions, let's unmute and thank Samrith for the talk.